So this video is going to go through and look at the applications of intra and intermolecular forces. So it is making the assumption that you already have some kind of basic concepts and ideas of what intra and intermolecular forces are, which is addressed in an earlier video linked there, which I don't think you can click on. But you can find it in that YouTube channel, and that would be the name of the video. If you are already in Mike's class, which should make sense to you if you were in Mike's class, then you would have seen the above video already in a play pause it before watching this. Okay, so real quickly, our types of forces. Our forces are intermolecular attractions, inter meaning between molecules. So inter, between molecules. And this is different from our intra-molecular attractions because intra means within molecules. So intra is within a molecule. One of the initial assumptions that we're going to make when we're talking about inter and intra is that if we looked at, say, a compound, let's call it water, the intramolecular attractions would be shown with these solid lines, okay, connecting the individual atoms. So the intra end up being bonds. The inter end up being kind of implied. An inter kind of requires another molecule to be drawn in. Okay, so if I were to draw in that second molecule, the intermolecular force would be the attraction between one molecule and the other. That is now an intermolecular attraction. Sometimes, okay, not always, shown as that kind of dashed or a dotted line connection between those. What we're trying to do is differentiate that from the intra being bonds. The intermolecular attractions are very often assumed that there are other molecules. So there's not an easy way for me to ghost without just straight up erasing. So I could draw out the water molecule and say, what kind of intermolecular force would water exert in its environment? In that case, what I'm asking you to do is to draw in a second molecule at least to establish what that intermolecular attraction is. So intermolecular is always between at least two different compounds or different molecules. That second molecule isn't always drawn, and in fact is rarely drawn, particularly in Chem 130. Okay, so with that intro, we could now look at our intermolecular attractions. There are three. We have your ionic or electrostatic, and as we talked about before, electrostatic is really just a way to differentiate it from the ionic bond, but it's effectively the same thing. The dipole-dipole intermolecular force, and the London dispersion, van der Waals, or I'm going to go ahead and add some extra terms on here. You can see induced dipole. This one's really irritating to write out, which is one of the reasons why I don't write it out. Induced dipole force. Probably the most accurate of the names. It's also the most tedious to go through and write out. Okay, but that name could also get used. You could even see it abbreviated as just an induced dipole force. So with that, we need to be able to identify each of these forces. So what I would recommend you do is pause the video and try and come up with a definition for each of these three things. If you've already got notes from the past video, don't look at those notes. What you want to try and do is pull back as much information as you can about these three types of intermolecular forces. So I'm going to again request pause, tap space, click the screen, and we're back. When we're coming back and looking at this, our ionic or electrostatic forces are ultimately going to come from ionic bonds. So what does that mean for me? Well, that means that when I look at an individual structure or formula, I need to be able to identify what kind of bond is connecting those. If I can identify that bond as ionic, then I know the interaction or the intermolecular force that this molecule will exert out on another molecule will be an ionic interaction. Okay, and so that's what we're trying to go through and do. Okay, for those of you paying attention, what we just did was defined an ionic force as an ionic bond. That's not a useful definition. I can't apply that. So how do I know I have an ionic bond? Well, I would know I have an ionic bond because I have a metal and a nonmetal. And when we look at sodium and chlorine, sodium's a metal, chlorine's a nonmetal. I now have an ionic bond. So that would allow me to tip off that I'm looking at ionic intermolecular forces. The next one down on the list is the dipole-dipole force. The dipole-dipole force comes from a compound that has a polar covalent bond. Okay? That would mean we have partial charges, and we have that is probably an unfortunate way of showing this. The Greek letter chi, capital Chi, is electronegativity. So we're looking for a large difference in electronegativity. So if I looked to identify a polar covalent bond, carbon to oxygen, okay, how do I know that's polar covalent? Well, that becomes a very challenging question. Okay, so we're defining that we have a dipole-dipole force with a polar covalent bond that doesn't help us out. The other thing we could look to would be the difference in electronegativities. But I'm going to bet none of you have memorized the electronegativities of carbon and oxygen, so we don't know the exact value of that. But hopefully what we can recall is that oxygen is the second most, meaning it is going to generate or pull those electrons towards it, which means the oxygen starts to become negative. Not formally negative, so I can't write it as just a negative sign. This is where I would introduce what is known as the delta notation. I'm using a lowercase delta to represent a forming charge, okay, or a partial charge. Well, if the oxygen's becoming partially negative, the carbon would be partially positive. In all of that, to be able to come to that analysis, I had to know something about those electronegativities. This is why when we talked about electronegativity way back when, we said it was an incredibly important concept that you need to be able to know. Okay? Which is then going to get us to kind of the next point. How can we trigger? What can we look for on this? And the definition right now that I'm going to tell you as your kind of rule of thumb is that it's everything else. Well, what the hell does everything else mean? Right now, it doesn't mean anything until we know what all of our other systems are. So we'll come back to that definition of everything else here in a second. The London dispersion or van der Waals forces, how do we know we have those? Well, those come from non-polar covalent bonds. I tend to abbreviate and just say covalent or polar covalent. So I'm differentiating between those two by adding the word polar. I don't have to add the word non-polar because now it's becoming redundant. This is a difference in electronegativity that is about 0. Okay, so what would our rule of thumb be for that one? Well, the first one's pretty straightforward. If it's 0, it's the same type of element to the same type of element. That would mean we have a non-polar covalent bond. If we have that non-polar covalent bond, that then means we have a London dispersion force when we look at how that molecule interacts with its environment. Okay, you'll note that it says approximately 0. It's not exactly 0. And that's because what we found through experiment is that there was another bond class, the carbon to hydrogen bond, that showed up so frequently in our molecules and compounds, but its chemistry was that of a London dispersion, or it acted very much like a London dispersion interaction, which meant that we had to kind of broaden the definition for nonpolar covalent to include the carbon to hydrogen. Now that we've got our 3 categories kind of defined out, we can double back to our everything else category. That everything else bond is really saying, look if it's a metal and a nonmetal. Really, all you have to do is look to see if it's a metal. Okay, if it's a metal, it's ionic. Is it the same to same? Then it would be nonpolar covalent. Is it carbon to hydrogen? Well, then it's nonpolar covalent. Everything else now comes in as the last stage. So you're really checking 1, 2, 3 things. If those 3 things aren't satisfied, then we're falling in the everything else category, and that by definition would then make it polar covalent and a dipole-dipole force. Is it perfect? No. Is it going to work? Yes. Okay, and so there will be some cases where that doesn't line up perfectly, but it works out pretty damn nicely. Okay. For those of you then being like, well, I thought there was another force. Okay. Isn't there another one? Yes, there is. We also get hydrogen bonding. The reason why I pull hydrogen bonding out is that hydrogen bonding isn't really a new force. Hydrogen bonding is a dipole-dipole force. It's just a special case of the dipole-dipole force. Okay, why is it so special? Okay, well, so first off, because we know it's coming from a polar covalent bond, because it's a dipole-dipole, that rule comes into play. The big thing that differentiates hydrogen bonding from dipole-dipole is this and, okay, which is why it's bolded. We're looking at hydrogen bonded to fluorine, oxygen, or nitrogen. Conveniently, fluorine is the most electronegative, oxygen is the second most, nitrogen is the third most electronegative element. Which means when we're looking at hydrogen bonded to any one of those three elements, we are looking at a difference in electronegativity that is massive. It is so massive that it starts to equate to an ionic bond. Because it's starting to mimic that, that now becomes a force that is somewhere in between the ionic and the dipole-dipole force, which is why hydrogen bonding gets pulled out as a separate thing. It also gets pulled out as a separate thing because of its importance. Hydrogen bonding is very commonly found in the world around us because it is found in water. Water is our classic hydrogen bonding solvent, and water makes up 70% of everything that we really experience. Okay? Because of that, hydrogen bonding got its own kind of moniker through this system. So how do we know we have hydrogen bonding? Okay, well, it's going to copy the rules of our dipole-dipole. It's going to be an everything else type situation. And more particularly, you will also have to see hydrogen actually bonded to fluorine, oxygen, or nitrogen. One big thing to note here is that if we're identifying that connection, that is a bond. That is a bond that is not hydrogen bonding. Okay? The term hydrogen bonding is a horrible moniker because it is not an actual bond. It's an intermolecular force. Okay, why do we call it bonding? Because it was so strong that people that initially discovered and addressed it started labeling the interaction incorrectly. And what they started labeling as the interaction was that bond connecting really hydrogen and fluorine. Okay, so they viewed all of the interactions and weren't able to differentiate between an actual intramolecular bond and an intermolecular force. Hence, we get the confusing moniker for it. It's a big issue. People have talked about it right and left, trying to change the name. The best that I can come up with right now is putting the bonding in quotes. More than likely, it's not going to change because there's now too many people using the term hydrogen bonding, and it's going to be too hard to re-educate the entire scientific community to change that name appropriately. Okay, so hydrogen bonding is not a bond, it is a force. Okay, which then gets us to the next big thing that we could go through. Well, almost next. Yeah, we'll do this. What we want to be able to do is have a rule of thumb. Okay, that rule of thumb is what's showing up in that red box. Okay, these are our thumb rules, if you will. Those thumb rules allow us to be able to look at a compound and be able to swiftly kind of classify the type of interaction that would be coming from it. That type of interaction, as we'll see here, becomes very important because we can use that to predict certain features. Okay, that prediction scale is the next kind of step that goes into this. We would also have to layer in the level of strength. The ionic interaction is a strong interaction. The London dispersion interaction is a weak interaction. And as was presented in the other video that you should have seen already, the London dispersion was such a weak interaction, we said it didn't exist. Okay. Then someone had to come along and be like, well, actually, it is important. We do have to address it. And that's what's happening. Okay. So when we're looking at this scale, we're going from the weak interaction all the way up to our strong interactions. Okay. As far as our intermolecular forces go. Okay. The thing that might you might start to notice is that an ionic bond generates an ionic force. A dipole-dipole bond, a polar covalent bond generates a dipole-dipole force. And a non-polar covalent bond generates a London dispersion force. So you'll probably start to see these kind of connections between them. I saw those connections as well and turned it into this kind of color wheel that's trying to represent the interplay between these. One of the things that is missing is that up at the top here, what we should be seeing is this color wheel stretching all the way from black over here to black over here, red through the middle. Okay, and what's happening is that we arbitrarily, as scientists, went through and cut a line through the middle of this and said that these were bonds, that says bonds, and that these were forces. Really, all that's happening is we have some level of attraction. Where we've decided that threshold is happened to fall right through the middle of our ionic interactions. This is why ionic bonds and ionic forces are very easy to confuse, because they're dividing. They're on the dividing line between those two categories of bonds and forces. So what I've effectively done is then kind of bent that down so that we can then see that interaction around it. Okay, so if we're going to add some extra information on these arrows, so this one around here is going to run all the way around, increasing strength of interaction. A non-polar covalent bond is incredibly strong. Okay, and we'll address some issues here on why that tends to be confusing for people. The non-polar covalent bond is the strongest interaction in this kind of argument. The London dispersion is the weakest interaction. Okay. When we look at the other arrow on the other side, we're saying increasing polarity, and that one's a bit misleading. That one should really run through the middle of this. Oh, that is one of the most god-awful looking arrows ever. Through the middle of this is our polarity arrow. Okay, the polarity arrow only goes up to ionic. Ionic is the most polar. Everything else is less polar, so that the arrows are a bit misleading on this. Okay, but what we're trying to do is show those connections, so that if I have, say, a black non-polar covalent bond, that's going to result in a black London dispersion force, so a very weak intermolecular force. And therein lies the issue with our non-polar covalent bonds. People go through and assume bonds are what are dictating all of our physical properties, and that is just not true. The physical properties are dictated by the forces. So that if I have a non-polar covalent bond, that is such a strong bond that that molecule doesn't want to interact with any other molecules. So we get a very weak force connecting those molecules to each other, which means when I go through to, say, boil it, I don't have to add a lot of energy in, and I phase transition very quickly. Okay? So what people are confusing is that difference between bonds and forces. They are both attractions between each other, but the strength of those attractions are vastly different, and they are interconnected. As we go through and make that intermolecular attraction weaker, say going up to or intramolecular attraction weaker, when we move up to a polar covalent bond, well, now that polar covalent bond isn't as strong within, so what does it need to do? It has to look outside to find something to stabilize it. So it's now going to generate a stronger intermolecular force to help neutralize those charges. Okay, so you could look at it as the non-polar covalent is so strong as a human being that they don't need others to succeed. A polar covalent bond would be someone that may be decently strong but needs some help. Okay, the ionic bond now needs lots of external help to help them succeed. Okay, and so when we're looking at classes and interactions and everything else in our world, that's a lot of what we see in our external environments. Okay, is how those physical properties manifest. Okay, so those are all the kind of properties that manifest out of this. If we were going to really call attention to the ones that become important for Chem 130, the phase transitions matter. We're looking primarily at melting points and at boiling points. Okay, melting point being solid to liquid, and boiling points being the liquid to gas. Okay, how do we make those transitions? Okay, the other one that's going to show up potentially for Chem 130 would be our vapor pressure. Okay, this goes back to our gas chapter, and it's the amount of gas that is naturally flowing to, the amount of liquid that naturally flows to becoming a gas. Okay, so there's nothing holding the individual molecules together as the liquid, meaning they have weaker forces. If you have a weaker force, your vapor pressure is going to be much higher because there's nothing holding it as a liquid. So it's going to transition to that gas phase more quickly and easily. Okay, viscosity is flow patterns, surface tensions, and then solubilities are going to be the big one. So we're looking at phase transitions, vapor pressure, solubility, and that's about it. Your textbook will address some of those other ones. They're all tied back to this concept of how those individual molecules interact with each other. If you have to propagate through more, or matriculate maybe is a better word, through more chemistry, organic chemistry is largely based on reactivity, and it all comes back to a hard application of these bonds and forces. So if you can pick up some of that kind of understanding of our bonds and forces, organic chemistry is really kind of simple. You're just trying to neutralize and minimize some of these interactions as your chemistry goes. Okay? And I'm sure lots of people can disagree with me. That's fine.